Welcome back to A-Star Tuition channel. Today we'll discuss about measurement, units, and uncertainties. Let's get started. Let's start with the notion of measurement. What is measurement? Okay, so a lot of you are probably not strange with the idea or the concept of measurement. So let's take for an example, like you have a sister and you have a brother. Now, if one person is, taller than the other, obviously taller, then you can see right away that, okay, the sister is taller than the brother. But what if they are of approximately the same height that you can't really tell which person is actually taller? Now, in that case, what you want to do is you want to compare the height of the two persons. Now, the act of comparing the height of the two persons is called measurement. Now, we can do that by using an apparatus like, ruler or tape meter to measure the height in this case to see which one is actually taller. Now, to define measurement, here let me write it down, is an act of comparing the same aspect of different objects of two or more different objects. Now, the aspect that we want to compare in the case of the example earlier is the height of the persons. So the same aspect, so the height for the brother and the height for the sister. Now, these are called, the aspect in this sense is called the quantities. Now, in physics, we usually refer to the height as length. Now, length is actually one of the 7 fundamental quantities that we will discuss after this. So, but then length itself can have different terminologies depending on what exactly that you're measuring. Like, for instance, if you're measuring distance from town A to town B, we call that length distance. And if we try to measure, let's say, when you look at this marker, this pen, so you want to measure how thick the pen is. Now that length of the thickness is what we call as the diameter. So length might have different various terminology associated with that, but at its core it's still length. So you can call it diameter, you can call it height, you can call it distance. So this or maybe the width of, if you want to measure, let's say how big or small your window is, you are talking about the width of the window. So they all have different terminology, but at the end of the day, we refer it in physics as the length, and we measure it in meter. Another aspect of what we usually measure in physics is time. Time is something that we measure in seconds. Although for some other occasion, it might be more appropriate to use like hour or minutes, or even days, years. But the unit or the fundamental unit for time in physics is second. Now, what other quantities that are of significance in physics? Now let's talk about 7 fundamental units in physics. Now, there are actually 7 fundamental units in physics, which we refer sometimes as the fundamental SI unit in physics. Fundamental SI units in physics. In other words, if obviously there are more than 7 quantities that we can quantify in physics, but then everything else actually is just a combination of these 7. Yeah. Now let's write them down one by one. Now, the first one is length. We already discussed about this. Length is measured in meter or m. And we also have time, which is measured in second or s, the lowercase s. This is lowercase m. And then mass. This is measured in kilogram, yeah, or kg. And then temperature. Temperature, the SI unit is in Kelvin. This one is capital, yeah, capital K. And then light intensity, which is which unit is candela or CD. And then the number of particle. This is measured in mole. And last is electric current. Electric current, yeah, electric current, which is measured in ampere, capital A. So there you have it. 1, 2, 3, 4, 5, 6, 7 fundamental SI unit in physics. So everything else is actually derivable from these 7. For instance, the notion of speed. Now this is measured in meter per second. So m over s or ms minus 1, this is the unit for speed, yeah, or velocity. And then we also have this example acceleration. ms minus 2, this is unit for acceleration. And then we also have unit for, let's say, force. That's kilogram meter second minus 2. Now, kilogram meter second minus 2, actually later you learn that this is abbreviated as M, aka Newton, because this is, Newton, or Isaac Newton is the physicist who actually discovered the Newton's law of motion. So the unit for force is dedicated for his last name, yeah, Newton. Now, this is unit of force. And there'll be like many more units that quantities that is derivable from these 7 as you go through all the topics in physics that we'll learn. Now, when you do measurement, sometimes the result that we obtain is numbers that are, very small or very large. Now, in that case, there are Greek prefixes for large or small numbers that you need to be aware of. Now, let me start with what if you have, let's say, something times 10 to the power of 12. Now, so if a number is multiplied with 10 to the power of 12, this is called 1 tera, or capital T, yeah, like 1 terabyte, 1 terameter, and 1 terasecond, or and so on and so forth. And then 10 power 9 is what we call as giga, 1 giga, or capital G, yeah, like 1 gigameter, 1 gigasecond, 1 gigagram, and so on and so forth. 10 power 6, 1 mega, or capital M, yeah. And then 10 power 3 is 1 capital K, lowercase k, 1 kilo. Now, the upper and lower case is quite important, yeah. So make sure that you use this exact case, yeah, whether upper or lower. For k, this is lower. for TGM are upper case. 10 power minus 2 is called 1 centi. Now this one is lowercase, 1 centimeter, centigram, and so on and so forth. And 10 power minus 3 is 1 milli, lowercase m, millimeter, millisecond. And then you have 10 power minus 6, 1 micro, micro. Now for micro, the symbol is a bit different. This is like mu, so please pay attention to the symbol for micro. And then you have 10 power minus 9, which is 1 nano, which is written in in lowercase n, 1 nano. Then 10 power minus 12 is 1 pico, lowercase p. Now this is usually used for the unit of capacitance, 1 picofarad. And actually there's one more, 10 power minus 15, which is 1 femto, or f. Now this is to describe the range of distances within nucleus, like the diameter of a nucleus, and everything else inside nucleus. Okay. Now these are not the only available prefixes. If you Google it, you'll find more. But then, in our subject of physics lesson in high school, these are the ones you need to know. Next is the notion of significant figures. So when you do measurement, sometimes you ask yourself, like, how many digits you should include. So when you include the numbers, the digits in your measurement, it actually pertains to what we call as significant figures. Now, what are significant figures? Significant figures tells you whether a digit within the result of your measurement is significant. Now, there are rules pertaining to significant figures. Now, the first rule is that all non-zero digits are significant. So, whenever you make a measurement and the result gives you the number, the digits that are not zero, those are all significant. Next is that all zero digits in between non-zero digits also significant. For instance, let me give you example for the first one. The first one, 1, 2, 5, 7. Now here, this is for significant figure. 52.85. This is also for significant figure. Now what about this bit? Let's say you have 4001. Now 15. Now you see that there are two zero digit and 3 non-zero, but the 2 zero digit are between non-zero digits. So here you have 5 significant figure, and then 5410007. Here you have 1, 2, 3, 7 significant figure. Now next is all zero to the left, all zero digits to the left of a non-zero digit, to the left of the first non-zero digit are not significant. So this one are not significant. Now example would be if you have 0.0075014. Now here you see that there are 3 zeros. These 3 zeros are actually not significant. So only 1, 2, 3, 4, 5, 6. So 6 significant figure for this one. Now what about all 0 digits to the right of the first non-zero digit in a decimal number? Now in that case, they are also not significant. Actually, sorry, they are significant. They are significant. So, for instance, if you have 1.4000, here you have actually 1, 2, 3, right? Now this is to the right of the first. They are significant. Okay, so there's a dot here. So this is 5 significant figure. However, what if you're dealing with an integer? Now, for 0 digits to the right of the first non-zero digit in an integer may or may not be significant. So how do we resolve this? Yeah, like, let me give you an example. If you have 1,500, now in this case, we can say that these 2 zeros are significant or not. It depends on whether you can write this as, if you write it in scientific form, can we write it as 1.500 times 10 to the power of 3? Or can we write it as 1.50 times 10 to the power of 3? Or we can write it as 1.5 times 10 to the power of 2 times 10 to the power of 3. Now, if this is the case, then this is actually only 2 sig fig. So in this case, this is only 2 sig fig. So the 2 0 behind 5 are not significant. Now on the other hand, if we have to write is in 1.500, then in this case the 2 0 are significant. So it becomes 4 sig fig. When we perform measurement, our measurement is always subject to uncertainty and error. Now what kind of uncertainty and error that you will mostly encounter in physics? Well, there are 2 types, two main types that you will encounter. The first one is called random uncertainty, and the other is called systematic. Now, what is the difference between random and systematic? Now, let's talk about the systematic one first. Now, the example of this one would be, say that you know that you weigh around 65 kilogram, and then one day, you try to measure yourself, in the bathroom scale, and then you find that the measurement gives you like shocking number, like 85 or 90, but you know that you haven't gained weight that much. So what's happening? It turns out that once you step out of the balance is actually measuring a non-zero value. So it means that even without no one or nothing on top of the bathroom scale, it still reads non-zero value. It reads maybe 20, for instance. Now in that case, if you measure 85 kg, that means your actual mass is actually 85 minus 20. That is because of the zero error or the systematic error. So the systematic error here happens because of the offset. Now the zero actually is zero error. Now the offset can also occur if you try to measure something by reading off like a ruler, but not at the right angle. So then it offsets your your reading, so it caused systematic error. So systematic error is a type of error that, as the word suggests, systematic. So something that happened because of error in calibration, or zero, the true zero is not the correct one, and also some offset. And you can fix this right away. Yeah. So in the example of weighing yourself in a bedroom scale, you know that it's not the correct zero, so you can just adjust so that the zero is exactly the correct number when no one is on top of the bedroom scale. Now, on the other hand, random error or random uncertainty is not as simple as systematic. Random error is something that is natural. In other words, if you keep doing the measurement multiple times, and you repeat the measurement, you will actually decrease the error. It's not like systematic. So if you haven't fixed the problem, it doesn't matter how many times you repeat the measurement, you will still get the same error. But random is different. This is due to variability in your measurement. So in order to decrease the variability, what you can do is you can repeat the measurement multiple times, and that way you can reduce this random error. In fact, the way to understand random error is this. Imagine that you can measure something infinite number of times. Now, if you measure something infinite number of times, the mean or the average of that measurement, that is the so-called true value of the measurement. Now, if you, let's say, do the measurement only 5 times, 6 times, 7 times, or maybe 10 times, then the difference between your mean and the actual mean from the infinite measurement, that's the random error. In fact, we can actually quantify random error by the so-called standard deviation. Now, standard deviation is a topic in statistics, in which you can calculate standard deviation by using this formula. So first, you do the value of each measurement, subtract with the average, and then you square it, right? And then you do the summation over all the data, all the data that you have. In other words, the number of measurements. And then you take the square root, and then you do, actually, you know what, before you take the square root, you find the mean of this first, and then you take the square root. So this is one way to quantify random error. Another way is like if you do a measurement once using a measuring device. Now there are 2 types of measuring device, analog or digital. So if you use the analog measuring device, then the uncertainty can be quantified using plus minus half of the smallest scale division. For instance, if you have a ruler and the smallest scale in the ruler is 0.1 centimeter, that means the uncertainty is half of that, which is 0.05 centimeter. And then what about if you have digital measuring device? Now, if you have a digital measuring device, the uncertainty is exactly 1 times the smallest scale division. Now, let's say if you have a timer, you measure time. Now, let's say that the smallest scale division is 0.1 second. That means the uncertainty in that measurement is exactly 0.1 second. Now let's talk about precision and accuracy. So two terms that might sound similar to each other but actually not the same thing. Now it's actually related to a concept that we discussed just now, which is about random versus systematic uncertainty. So imagine that you have a dart game in which you throw dart, and let's say that there are 4 players, and these are the result of the 4 players. Now the first player, as you can see, throw the dart at multiple locations. A couple hit quite near the center. So in this case, we say that it's quite accurate but not precise. Yeah, because accurate means that you can see that some of the dart actually land near the target. Yeah, so this is called accurate but not precise. Not precise because they are all over the place. Yeah, so like sometimes it's out, but then sometimes it's inside, so it's all over the place. So accurate but not precise. Now the second player, as you can see, it's kind of consistent, right? So then when you throw the dart, it always lands in this area. But actually this is not exactly the target. It's quite far away from the target. So in this case, we say that the measurement is precise but not accurate. Yeah, so meaning that this has a big systematic error, but not random error, not much random error, because the measurements are close to each other. So the result is close to each other, but it's actually far away from the actual true value. So precise but not accurate, meaning that in this case you have large systematic error, yeah, and small random error. Now in the previous one, it's accurate but not precise. We have a small systematic error but large random error. So you can see that some of the measurement or some of the dot land quite close to the target. Now the third one, and now you can see that here the measurement or the dot lands very close to the target, and there are also one dart and the next dart are close to each other. So this is what we call as a measurement that is both precise and accurate. Yeah, so in this case you have a small systematic and random error. Now on the other hand, the fourth player, as you can see, not only do they miss the target entirely, it's all over the place. So this is a case of not precise and not accurate. So with this illustration, I hope you can understand the difference between precision accuracy as it pertains to random error and systematic error. Next, let's talk about the uncertainty of calculated quantity. So let's say that you measure two quantities, let's say x and y, and there is another quantity, let's call it a, and a is equal to x times y. So here what you did is you measure x with its uncertainty, you measure y with its uncertainty. The question is, how does the uncertainty of x and y factor in the uncertainty of a, in which you calculate from the product of x and y? And there is also another type of calculated quantity. Let's say b is equal to 2x minus 3y. Now the question is, how do you quantify the uncertainty of b from the uncertainty of x and y? Now let's talk about it. Now the first thing we want to discuss is, what if the quantity calculated is calculated through plus or minus operation? For instance, if a is equal to 2x plus 3y, or let's say b equal to 2x minus 3y. Now let's say that x is measured and it has its own uncertainty. Let's say x is measured as x measured plus minus delta x, which is the uncertainty of measuring x, and y equal to measured with ym plus minus delta y. So how do we calculate delta A and delta B? Now the rule is simple for A first here. Delta A, now just look at the formula, 2x plus 3y. So delta A, or the uncertainty in A, is equal to 2 delta x plus 3 delta y. Now this is called the absolute uncertainty of A. Now we can also calculate the fractional uncertainty of A, which is delta A over A. Now this is simply equal to, in this case, 2 delta x plus 3 delta y over A, which is 2x plus 3y. Yeah, so this is called the fractional, or sometimes called percentage uncertainty of A. Now what about for B? Now for B, now as you can see here, the difference between A and B only with this sign. But as far as uncertainty goes, delta B is actually the same as for A, which is 2 delta x plus 3 delta y. So remember, whether this is plus or minus, add or subtract, the uncertainty or the absolute uncertainty is still positive. Yeah, so please bear this in your mind. Remember, this is the absolute uncertainty of B, and from here you can measure, you can calculate the fractional uncertainty of B, which is 2 delta x plus 3 delta y divided by 2x minus 3y. Yeah, and this is the fractional or percentage uncertainty of B. Next, let's look at the uncertainty for calculated quantity that you calculate through multiplication, division, and exponentiation operation. Now, let's say that new quantity A is equal to 3x times y. Now, the first thing you can do is, the rule is this: you cannot calculate the absolute uncertainty first, unlike the one previous, but you calculate the fractional or the percentage uncertainty. Delta A over A is equal to delta x over x plus delta y over y. Now, notice that this 3 here, or any constant that you have here, is actually not significant, and it's actually not affecting the percentage uncertainty. And once you have this, then obviously the absolute uncertainty can be obtained from delta A over A, which is this. Yeah, you multiply with A itself, which is 3xy. Now, what if you have another quantity B equal to minus 5x over y? Now again, the minus 5 actually not used to calculate the fractional uncertainty. So in this case, delta B over B is also delta x over x plus delta y over y. And again, delta B, or the absolute uncertainty of B, is simply the fractional uncertainty, which is delta B over B times B. And remember, delta B over B can be calculated from here. in which the delta x and delta y are given, yeah, is what you measure. So then what is the difference between this and that? Now, it turns out that it's actually the power that is the key here. Like here you have x power 1, y power 1. Here you have x power 1, y power minus 1. Right? Now, what if you have a different power? Let's say you have c equal to x power 3, y power 5. Now in this case, so this is exponentiation, x power 3, y power 5. The fractional uncertainty of c is 3 delta x over x plus 5 delta y over y. And then as like before, you can calculate delta c by multiplying this with c itself. Yeah. Now what if you have another quantity d, let's say x power 3, and then divide by y power 4. Let's say x power 7. Yeah. Now in this case, delta d over d, the fractional uncertainty of d, is equal to 7 delta x over x plus 4 delta y over y. Now you can see that what we use is the power of x and y of the measured quantity, and the power is always positive. So even though it appears in the formula as negative power, so remember this is y power over y power 4 means y power minus 4. It always appears as plus 4, right? So that in general, let me write down, in general, yeah, for calculated through division, multiplication and exponentiation, if let's say you have a formula of a quantity as x power alpha, y power beta, and let's say another variable, remember the variable is not restricted to just 2, yeah, power gamma. So let's say you have a quantity that you measure, x, y, t, with its own uncertainty, and then you can calculate the uncertainty for this measured for this calculated quantity z, the percentage uncertainty or the fractional uncertainty to be exact, as absolute value of the power of x, which is alpha, times delta x over x, plus absolute value of the power of y, which is beta, delta y over y, and then plus absolute value of gamma, delta p over t. Now obviously you can expand this if you have more than 3 quantities that you measure. So that's it for our lesson this time about measurement, unit and uncertainty. These are actually a very important basic knowledge that you need to know in physics. I hope this lesson, this video helps you a lot. Don't forget to like, subscribe to our channel and share. I'll see you again next time.